Okay, so welcome everybody back to this webinar organized by the Women in Radio Science chapter of the URSI-Spain. Now we are delighted to host a motivational talk by Professor Dame Jocelyn Bell. I would like to thank our sponsors, the COIT, the Official College of Telecommunication Engineers, and the OESIA Chair of Vigo University. We said before, but just to remind you that we are recording the webinar. This week is the students in Spain are going through the A-levels, the equivalent of the A-levels. And many of our colleagues from the universities are busy with these exams. So that's why we wanted to have a record of this important talk. At the end, we are going to give the audience the opportunity to make questions. And please raise your hand to speak or write it in the Q&A area. I just want to do a brief introduction. Excuse me, this doesn't, excuse me. I don't know what is happening, but it's not. Just a second that my slides are not advancing. I'll try again. I think I'll leave it in, let's see if it works in presentation mode. Yes. Okay, so a brief introduction about the Women in Radio Science chapter in Spain. Just wanted to introduce you our team. I'm so lucky to have the help of Elena Abdo Sanchez as co-chair of the chapter, but she's also president of the Spanish Commission B for Bills and Waves in URSI. She works in the Malaga University. Our secretary is Rocío Sánchez Montero, and she works in the Alcalá de Henares University. And the treasurer is Miquel Lasso, that is also the URSI-Spain president from Navarra Public University. I ask the audience to please join our efforts. If you like what we are doing, please send us an email to that address below. Okay, so I just wanted very briefly to tell you what we are trying to achieve in the chapter. And we want to support the Spanish girls and women in achieving personal development and success in this in radio science. So we would like to have a more inclusive and egalitarian society in Spain with reduced stigma and have greater freedom of choice for everybody and proper recognition, professional recognition for all. Among our objectives are to awaken science vocations in girls and women, support the continuity of women in their professional careers, increase the representation of women in science and technology, mostly in the URSI organization. We want to share our enthusiasm for research and experimentation and combat the myths and misconceptions that are so normal, unfortunately, today in science in the society. And among the actions we are putting in place are this award for the best initiative to promote female vocations in radio science. This has been the second edition this year of this award, which just decided the winners. We just announced them. And other actions are like this webinar, organization of Conference of Women in Radio Science, and webinars featuring outstanding women like the one we are so lucky to have today. Mm-hmm. So just let me introduce our speaker. Jocelyn Bell has had an astounding career devoted to science, but mostly, very important for us, is the advocacy for women's role in science. So she inadvertently discovered pulsars as a graduate student in Cambridge, and that discovery was recognized with a Nobel Prize that was awarded to her supervisor. This has been one of the most important astronomical discoveries in the 20th century. This was a new type of star, neutron star, that has provided insights into how stars, the nature of stars and their evolution, but also help us understanding other exotic objects like stellar mass black holes. So more than 50 years after the discovery of pulsars, today we are still using them as a powerful tools for testing extreme gravity and general relativistic effects. The pulsar timing arrays are using them to detect gravitational waves, the gravitational wave background, what they call the hum. And still today, the astronomers are puzzled with this new type of pulsars, magnetars, that have so strong magnetic fields, stronger than 1,000 times a normal pulsar. So SIS has worked in many roles, in many branches of astronomy, and working part-time in some occasions while raising her family. She's been president of the UK Royal Astronomical Society, the first female president of the Institute of Physics in UK and Ireland, the first female president of the Royal Society of Edinburgh, and she received the Special Breakthrough Prize in Fundamental Physics and won a $3 million prize. With this quantity, she has established the Bell, instead of going on vacation, or retiring, she has established the Bell Burnell Graduate Scholarship Fund. And she was one of the few women that set up the Athena Swan Scheme for research institutes to promote equality in research institutes. And nowadays she's visiting academic in Oxford in the Department of Astrophysics. And just wanted to share with you all the impact and recognition that we do to her figure, to her legacy in Spain. In the Public University of Navarra, they have an educational radio telescope that has been named after her. She received the medal gold of CSIC, that is the Spanish National Research Council. She has a star in the Santa Cruz de la Palma Science Walk. In Jeves Observatory, where I work in the town, we have the primary school is being named after Jocelyn Bell, and the students there have the opportunity to firsthand learn about pulsars and participate in a fair that is organized every 2 years about astronomy, Expo Astronomica. In Jeves Observatory, the International Day of Girls and Women in Science is centered around pulsars and Jocelyn's figure. And the closest high schools to our observatory, like the Brianda de Mendoza, has Jocelyn Bell as role model. And there you can see a student dressed up like her. We've also been participating in the setting of a baseline project funded by IAU and SKA, where students learn about radio astronomy, and a group of students were learning about the pulsars and presenting a project. And well, many more. This list is not exhaustive. So without any further delay, let me hand over to Professor Jocelyn Bell. You are very welcome. It's a pleasure to have you here, that you join the URSI community, and mostly the Women in Radio Science chapter. Thank you very much, Jocelyn.
Thank you, Christina. Am I heard okay?
Perfect. I'm going to stop sharing.
So I have a short PowerPoint presentation telling you about what happened when I was a graduate student and accidentally discovered pulsars. My accent is not standard English, and I apologize for that. I come from the north and west, so my accent is more Scottish than English. But I found myself in the south of England, in Cambridge, doing a PhD. And that was quite scary for someone from the north. So I will talk just a little bit about working in an environment where I was in a minority. I started life in the north of Ireland. I failed the first important exam, but was allowed to do science and next year came top of the science class, beating everyone who had passed that exam. So something funny there. I had most of my high school education in England at a girls' boarding school where they had trouble getting good science teachers. But we were very lucky with our physics teacher. He was very, very good. I went to Scotland, to the University of Glasgow, to do a physics degree. I ended up the only female in a class of 50, 49 men and me. And none of the men would work with a woman, so I had to solve all my own problems. And then I went to Cambridge for a PhD. So showing you.
Let's see something.
Wow.
Hey, wonderful.
Great.
It worked.
Whoa. Not sure what went wrong there, but okay, we're working.
Yes, you see, at the end it works.
Does that one work?
Yes, yes.
Oh, good. Okay. So sorry to have taken so long to get all this working. I
No
wanted
worries.
just to tell briefly the story of the discovery of pulsars, which happened when I was a grad student. And if I don't take too much time on that, I will also talk about some instances where pulsars were nearly discovered, because I think that also tells us a lot about how science works. So I started life in provincial Britain in the north of Ireland, failed the first important exam, but next term came top in the science exam, doing better than all those who had passed the exam I'd just failed. And I had quite a lot of my education outside Ireland in England at a girls' school. And girls' schools often have trouble getting good science teachers. I did a bachelor's degree in the University of Glasgow. It was heavily male dominated. Our class was 49 men and me. And none of the men would work with the woman, so I had to solve all my problems myself. I then went to Cambridge in the south of England to do the PhD in radio astronomy. And this was a very different place from Glasgow. It was full of young men, very confident young men, walking around the streets in small groups, talking in loud voices about what Pliny had said or what Pliny had not said. And I really felt that I was from a different country. And yes, I had been in the north of England, and there is a gradient in our country, particularly enforced by people in the south of the country. People in the south of the country are civilized. People in the north of the country are not civilized. My first day in Cambridge, I am given a set of tools. I still have them. These were my first tools. And they are not microelectronics tools. They're big, full-size tools. And I spent 2 years helping to build a radio telescope. The weather in England in wintertime is not nice. We are all wrapped up against the cold. I have been putting plugs on cables. And because the cable could not be coiled up and taken indoors, I worked in this little hut and that little hut at the other end of the cables. We're building a very big radio telescope. There's 192 kilometers of wire and cable in this radio telescope, and it has an area of 57 tennis courts. It's big. It took 6 people 2 years to build it. This is the finished radio telescope. Because it works at low radio frequencies, you do not need to make a dish, a solid reflector. You can use strands of wire. It had an area of 1.8 hectares. That's 57 tennis courts. And it contains a lot of copper and other wire and wooden posts. And it is pre-transistors. There were some transistors then, but they were very new and very noisy. So we continued using vacuum tubes, or what in Britain we called valves. My project was to find the objects called quasars, quasi-stellar radio sources. They were very new and the hot topic then. The early radio astronomers had found some very strong radio emitting sources. And the optical astronomers said, there's a curious star-like object at that point in the sky. And they couldn't really make sense of it until Martin Schmidt and Jesse Greenstein, who were looking at some of these early spectra. Martin suddenly thought, this spectrum looks like tellurium, but it can't be. Maybe it's hydrogen with a very big redshift. So he went to Jesse Greenstein, who had spectrum of another of these objects, equally puzzling, and said to Jesse, could it be hydrogen with a large redshift? And they both agreed that their spectra worked well. And that was the identification of the first quasars as very distant objects. Now, the project I had a good way of picking out quasars from amongst the other radio emitting objects in the sky. And I won't go into this detail, but it hinged on the fact that quasars are compact, very compact, and other radio sources are not. At that time, the University of Cambridge had one computer. It used vacuum tubes, not valves, and it took up a whole room, and it had less memory than your laptop. So clearly very few people could use it, and I did not have time on that computer. All my data is analysed by hand, and this is some of the data analysis going on. There was a lot of this paper chart, 30 meters every day. And I observed for 6 months, so I had over 5 kilometers of paper, like in the picture. I was repeatedly surveying the same sky to look for quasars, and when I found them, to get a measure of their angular diameter. I won't go into all the details, but important for this story is that I was using a short integration time constant integration time of 1/10 of a second. And I spent 2 years building the telescope and then observed for 6 months. And I found many quasars. It worked well. But along with the quasars, there was there was quite often radio interference. This is a piece of radio interference. This, I think, is the very first pulsar signal. And if you look at these two signals, which concentrate on the higher frequencies, the lower frequencies have been cast aside. They look different. Here the spikes go up and down. Here the spikes go mainly up. Here you can see space between the spikes some of the time. Here on this bit you can see no space. When we do that kind of comparison, we are actually doing Fourier analysis. we are asking what frequencies are present in these signals and what amplitudes are present in these signals. So this is Fourier analysis by eye. And I didn't know what this was, and nor did my thesis advisor. He said, well, keep observing. And I kept observing, and this signal, where's my cursor? Lost my signal. All right. This signal was not always there, but when it was there, it was at the same position, the same right ascension and declination from the same point of the sky. Whereas radio interference is produced by something terrestrial, and that does not keep constant, does not appear to have a constant sky position. So my thesis advisor advised me to expand the recording, run it faster, run a high-speed chart recording. And on this image, you see time signals, 1 second time marks in the lower trace, and in the upper trace, pulse, 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 maybe one missing, pulse, 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 maybe 3 or 4 missing, little one, little one, little one. And they are spaced at about 1 1/3 seconds. Well, my supervisor thought it was interference, thought I had wired something up wrong, but next day came out to the observatory and watched as I set up for this observation and saw the pulses for himself. The most likely source of these pulses is because somehow Jocelyn has wired the radio telescope up wrong. Some wires have got crossed or something like that. What we really need is to see if another radio telescope can see this signal. And there was another radio telescope working at that frequency at the observatory. And we asked the grad student on that, Robin, and his supervisor, Paul, very quietly, could they help us check, see if their radio telescope could pick up this signal? And I remember that day very well. The way the two telescopes were aligned, my telescope saw it first, and then Robin's would see it. And my telescope saw it well, good and strong. And then we went and stood by Robin's chart recorder, and nothing happened. And the two academics started walking away saying, what could it be that shows in this radio telescope but not in that one? Could it be this? No, it can't be that because da 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 da. And I'm following behind them trying to keep up. Robin stays by his pen recorder. And we get down the end of the long lab and suddenly there's a shriek from Robin, here it is! And we all race back. And we see it on Robin's telescope and Robin's chart recorder. Robin had miscalculated by 5 minutes when his telescope would see that object. If he'd miscalculated by 25 minutes, we would have all gone home and the story would be different. So it's not to do with my radio telescope. It's outside, beyond my radio telescope, because it's seen by another radio telescope with its own receiver. So, Jocelyn, keep making these recordings. And Jocelyn, keep going on the main thesis observations and the data analysis for the main thesis observations. So I was busy, but I did all those things. I've talked about it not being radio interference. I've talked about it being seen by a separate telescope, but it was striking from the beginning that the pulses were quite short, so the object must be small, or more precisely, the pulses have steep sides, so the object must be small. But it's also becoming clear that the pulse period, I'm measuring it to 6, 7 decimal places, and I can't see any change. So it must have big reserves. It's not getting tired. It's big and it's small. Yippee! How clear, how wonderful. We managed to get what we call a dispersion measurement. We got 2 receivers tuned to slightly different frequencies. And as the signal, a radio signal comes in, it descends in frequency. And so the high frequency receiver sees it first, bang, and then the low frequency one sees it later, bang. And the time between those 2 bangs, the dispersion, can give you an estimate of the distance if you know the electron density in space. We don't know the electron density very well in space, but we could make a guess. And the distance came out to be 200 light years. So it's not in the laboratory in Cambridge. It's not anywhere else in Cambridge. It's not in Europe. It's not on the Earth. Its source is even not in the solar system. It's away out in the galaxy. Well, I had nicknamed these objects little green men, and now we had to seriously think about this. Could this be another civilization signaling to us? And in English, we tend to refer to extraterrestrial people as little green men. So if it is little green men, they probably live on a planet that goes round their sun. And some of that time, the planet will be coming towards us, and some of the time it'll be moving away from us. And there'll be a Doppler shift on the pulse period. When it's coming towards us, the pulses will pile up. When it's moving away, the pulses will be further apart. So, Jocelyn, keep observing the pulse period, which I did, but we could not find any Doppler shift. Fortunately, then, I found a second one, and a third one, and a fourth one. There might be one lot of little green men signaling to planet Earth, but there's not 2, 3, 4 lots of little green men signaling to planet Earth. This must be something astronomical. So we carried on working. I found a second, a third, and a fourth, and we were then in a position to publish. We know it's astronomical. We don't know what it is, but we know it's not little green men, and it's not something on planet Earth. So we write up the first one for a paper, send it off to Nature. Tony gives a colloquium in Cambridge. Every astronomer in Cambridge comes to the colloquium. Tony's favourite picture was of a white dwarf star oscillating and somehow launching shocks, which gave pulses. But when Tony gave the colloquium, Fred Hoyle was in the audience, and Fred Hoyle did not like this model. He said, no, it's rotating. You can tell the difference when you measure the period derivative. And it turned out that Fred Hoyle was correct. They are rotating objects. And as rotating objects age, they gradually slow and stop. Whereas a vibrating object, as it ages, gets faster and faster and faster and faster. But the amplitude gets smaller and smaller. So this had to be a rotating object. However, that wasn't clear at the time we published. And when Tony gave a colloquium in Cambridge to announce this discovery, every astronomer came. And at the end of the colloquium, Fred Hoyle, famous British astronomer, cosmologist, was the first to speak. Tony was favouring this vibrating model, and Fred Hoyle said, no, It's not a vibrating object, it's a rotating object. And his physics instinct was absolutely right. It did turn out to be rotating object. We had given some thought about what to call these things. We could have called them pulsating radio stars or pulsed radio stars. Pulsed might suggest there is something making the pulses, little green men. So we said firmly these are pulsating radio sources. But the newspaper science correspondent said that's too long. And he invented the word pulsar. And pulsars, they have been known ever since. Now, one of the nice things about having discovered pulsars is every so often somebody comes up to me and says, you know, I nearly discovered pulsars, and tells me the story. And I'm going to tell you some of those stories now, because they show us a lot about how science works or doesn't work. The first instance is way, way back in 1957. We are in the United States of America at the McDonald Observatory. The McDonald Observatory is open to the public one night every month, and it's the public opening night. And the telescope is trained on the Crab Nebula, and in particular on the star in the center of the Crab Nebula, which was believed to be the remains of the star that went supernova and produced the nebula. We now know it's a pulsar flashing at 30 times a second. So members of the public step up to the telescope and says, oh, wow, or gee, or whatever people said in 1957. And a young woman steps up to the telescope and says, that star is flashing. And the night assistant explains about scintillation and turbulence in the atmosphere, etc., etc., etc. And she stops him and says, no, I know about that. I am an airplane pilot. My job is to fly newly built aircraft from the manufacturer to the customer. I fly at night. There's not a lot to do in the cockpit at night, and so I look at the stars. I know about the scintillation of stars caused by the Earth's atmosphere. This star is different. This star is flashing. Now, we now know that the star in the middle of the Crab Nebula does flash. It flashes very fast, 33 times per second, which is close to the limit of the human eye and brain. But some people, especially young women, can see flashes at 33 hertz. There's good evidence on this because in Canada, the main power supply used to be at 33 hertz, and a number of young women could see their lights and everything flashing at 33 hertz. So some people, especially young women, can see 33 hertz. So I believe she saw the Crab pulsar flashing in the optical, but nobody took much notice of her except for the summer student who made a note, wrote an account of the incident. Another story about failing to discover pulsars earlier. It comes from an American who probably is no longer alive. He worked for the American military. He was posted to Alaska, where he was looking out for missiles coming in from Russia, from the Soviet Union. He's at a ballistic missile early warning site. It's fairly quiet. His boss allows him to play around with the radar receivers if he wants to. And so he's turning these radio receivers around the sky, and he finds a flashing source. He did an astronomy course at college. He knows about right ascension and declination, and so he makes a record as best he can of the right ascension and declination of that pulsing source. And then he finds a lot more, and he ends up with 14 of them. But he's on a top secret site. He's not allowed to publish. Illegally, he makes a note on a little piece of paper of the right ascension and declination of these 14 pulsing sources that he's found. And he has just discovered the online catalogue that the Australians keep, the online pulsar catalogue. And 10 or 11 of his 14 sources are pulsars. If he had not been working for the American military, he would have been allowed to publish, if any journal would accept such a paper. But it seems fairly clear to me, going back a slide or two, that in 1967-68, about the time I was discovering pulsars in Cambridge, he was discovering pulsars using the early warning system in Alaska. I was allowed to publish, he was not. He came to a number of our pulsar conferences, got very excited, and had a wonderful time. Another example of a near miss involves Sue Simpkin. Sue was brought up in Canada, and when she was a child in Canada, the mains power supply for the lights and things was at 33 hertz. So she could see the lights flashing. She was one of those young women with the acuity to be able to see 33 hertz. She says it nearly drove her mad, and she was quite glad to get out of Canada. So she's an astronomer now. She's an ultraviolet astronomer, and she has time on the Kitt Peak telescope. And eminent Dutch astronomer Lo Vulture asks her to take an ultraviolet spectrum of that funny star in the middle of the Crab Nebula, known as Minkowski star. Sue does that. She says the spectrum's pretty dull, but as she's making the observations, she can see it flickering. Said it was as if there were waves going out from it. When she told Lo Vulture this, he said, no, it can't be. But when it was discovered that that star was a pulsar, he was man enough to say she must have seen it in the ultraviolet. The final example, I'm not going to name the people involved because they were very embarrassed by this story. They are a group of radio astronomers surveying the sky at 408 megahertz using the largest telescopes they can. And so they get a bit of time on that big telescope and a bit of time on that big telescope and a bit of time on that big telescope. And they've almost completely surveyed the sky, but there's a few little bits they still have to observe. And it's of an era when they were still using pen recordings before data went into computers. And one of the pen recorders was a bit sticky. It occasionally jammed. And in the early hours of one morning, about 3 a.m., that wonderful time if you're an astronomical observer, that troublesome pen recorder started going wheep, 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 wheep. And the observer said, damn it, and did what you did to troublesome pen recorders, you thump it. So he thumped the pen recorder and it stopped going wheep, 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 wheep and went back to its normal behavior. And he said, good. He put on his coat and he went home to bed. It was 3 o'clock in the morning. He did not make an entry in the log book. He had actually been observing the pulsar 0329, not at that stage discovered. And if he had made an entry in the logbook, he could have claimed prior discovery. This is why we have logbooks, lab books, and why students are forever being told, put it in your logbook. However, so that story came to light. What I also find a little bit sad is following the discovery of the first pulsars, the announcement, those radio astronomers did not go back through their data. They had surveyed the whole sky, north and south, and they didn't think to search their data for pulsars, which was also a bit sad. My final point doesn't involve any of these near misses. It involves the insight of an Italian astrophysicist, Franco Pacini, alas, no longer with us. One of the problems exercising people at the time I was discovering pulsars is, why is the Crab Nebula still shining? We know that the Crab Nebula is the remains of a star that exploded in 1054 AD. 1054 is quite a long time ago. Why is that nebula still shining? Why has it not gone dim and become very hard to see? Well, we now know it's because there is a pulsar in the middle of the nebula. The star that exploded, most of the material went out to make the nebula, but the core remained and is a pulsar whizzing round very, very fast. But that wasn't known at that point. But Pacini wondered, suppose there was a very compact star left over from the big explosion that created the nebula. Supposing that star had a very strong magnetic field. Suppose the magnetic field was inclined to the spin axis so that it cones around. Then you could get magnetic dipole radiation from this spinning dipole. And that radiation is probably of a frequency that cannot escape from the nebula, so the energy gets dumped in the nebula and keeps the nebula shining. Franco Pacini was 100% right, even 110% right. I want to finish by saying just a little bit about what I think were the factors that led to the discovery of pulsars at that time. First of all, I had my own telescope. Well, it was my supervisor's telescope, but I used it, and my own receivers. And I understood its behavior very, very well, having worked with it and got lots of data off it. I'm a graduate student, so I have time and space to follow up anomalies. Indeed, grad students are meant to follow up anomalies. And remember, I feel an outsider in Cambridge. I know I'm not bright enough to be in Cambridge. I know they've made a mistake admitting me. I know they're going to discover their mistake and throw me out. And my policy is to work as hard as I can until they throw me out. So I'm working very, very hard, very, very thoroughly. This was one of the first observations with high time resolution, with a short time constant. Mostly people use longer integration times because you got better signal to noise. And the final factor is less important, but we were not aware of other observers with similar equipment. So we believed we had a clear run. And so we took the time to be absolutely sure that what we were announcing was correct and true and right in every possible sense. It also helped that we were Cambridge. We had a good address. If you are going to make an outrageously new discovery, that's hard if you're not at a place that has a good reputation. Today, funding bodies like research councils ask you to say, what do you want the money for? What are your objectives? What are your targets? That wasn't the case when I was working, but if it had been, in pursuing this observation, I was going off target. This was not one of my objectives. It could not have been, because we didn't know these things existed. Would we have been penalized for not sticking to the program we said we were going to do and doing other things as well? If we had computerized the search, computer memory was almost non-existent then, was always going to be limited, we probably would not have programmed the computer to look for anything like this. And a slightly different remark, working at low frequencies. Low frequencies has long been a neglected domain in radio astronomy. There's more now, but it was largely ignored at that time. And the time domain was ignored because you needed fantastic signal to noise, which you normally could not get. So with an image of the Crab pulsar flashing, I will stop talking there. Over to the chair, Christina. Maybe we've time for questions, maybe we don't. Anyway, over to you.
Thank you very much, Jocelyn. I've enjoyed tremendously, and I'm sure our audience as well. And thank you very much for sharing these wonderful stories. And I'm sure it has been so inspiring for our young female scientists, these girls that are doing now their PhDs. It's been amazing. Thank you very much.
Thank you.
Okay, any questions from the audience? Gianni Baños is saying fantastic. So while they start making questions, so you've been in very important positions with lots of responsibility, and we know that you've been sharing also motherhood, so you had family responsibilities. What do you recommend to our young scientists today? You know that they are facing. So we are seeing that many of them finish their PhDs, but after that, it's difficult for them if they want to start a family. So what would you recommend them?
Yes, it is combining being a mother and being a scientist is very difficult. Sometimes universities will let you work part-time, which helps. But even then, there is the little voice in the morning that says, "Mummy, I feel sick." And you know your day is gone. It's really hard. You need a very sympathetic boss. You also need a husband who will help. And sometimes the bosses of husbands are not so flexible as the bosses of women when there are children. So more often it is the women who take time from work than the men. But yes, it does disturb your career a lot. And also there are the questions of how you get jobs for two people in the same place, in the same city. Often somebody has to compromise. And since the woman is the one whose career is broken by giving children, having children, often it is the woman who compromises. Not good, but I don't have a solution except marry a good husband.
So, you know, that's my experience. So yeah, having someone that supports you and help you when you have to travel, take care of the children while you're away. And I completely agree with you. So we
And
have
somebody that can cook.
So Raquel Gomez is saying, amazing. Clara Iglesias, thank you very much for your inspiring talk. Pablo Mateos, incredibly inspiring and illustrative talk. Thank you very much. Leonora, Ana, in Spanish, many thanks for this talk. So inspirational and magnificent. So any one of our panelists would like to ask something to Jocelyn?
Can I?
Sure, Mikkel.
Well, hello. So thank you very much in the first place, Professor Bell. It's really hard to ask questions after such a brilliant presentation because you can read it all. Thank you very much. Thank you for being an example to all of us, men and women alike, and for also being a model of dignity in the practice of our profession as radio scientists. I want to make a general question. I suppose the publication and conference system has changed a lot since you started working until now. How do you view the system nowadays? Has it really changed?
Now that there are online options, you can attend a conference in person or online. It makes it a lot easier if you are a mother with a child that is sick. So you have to be at home and you cannot be at the conference. So COVID, in that sense, gave us more options, showed us more options, which I think is a great help. It still remains difficult to get good jobs for two people in the same place. And society, I think, I don't mean astronomical society, I mean society at large, still assumes that it is the woman whose career is put on hold or slows up when there are children. So we are much better, much, much better, but I think it's not yet parity. It's still a bit, like that.
We have another comment, Gisela, many thanks, Jocelyn, very inspiring. And a question from Francisco Colomer. So it is okay to have the imposter syndrome?
I suspect actually a lot of people have imposter syndrome, particularly when you're younger and starting out. But in Britain, it is never talked about. And I think that's unfortunate. So I talk about it. Because I'm sure there will be other people, probably other women in physics departments in particular, or engineering departments, where there are very few women who may feel they are imposters.
Yeah, like the outsiders that you've been talking about before. But also, I've heard you saying that it's so good to have these people from different backgrounds, from different
Yes.
contributing to the effort.
Yes, you do better science. You do better science if there are many ideas coming in from different angles.
Yes, yes,
Yeah.
yeah, definitely. Any other question from our panelists before we close? Yeah, Lianet, go ahead.
Yes, well, first of all, Professor Jocelyn, I'm truly excited. It's very difficult to make questions, as Mikkel said, because I'm left speechless. So emotional. Yes, you are such an inspiration. You are brilliant, and and at the same time, so incredibly humble. At the same time, but I would like, if it is possible for you to tell us more about your experience being the only one among 49 men in the class. How did you feel at those times?
Yes. Well, I was living in a woman's dormitory. And when I came home on the first day of term and said, it looks like I'm the only woman in the class, all the other women in my dormitory said, oh, you'll be changing subject then. at that stage, I already knew I wanted to be an astronomer, probably a radio astronomer, because you don't have to stay up at night if you are a radio astronomer. And I like my sleep. So I had my sights on being a radio astronomer, and to do that, I need this physics degree. So when the women in my hall of residence say, "Oh, you will be changing field then, Jocelyn," I go, I can't. But clearly also not much support from the women I'm living with, because they all think I should change. So it was quite lonely. It was lonely in the dormitory. It was lonely in classes. But I was lucky in that I knew what I wanted to do. If I hadn't, oh, I'd have done biology or something. Thank you.
Thank you so much. Thank you. Very inspiring.
We have a last question. Elena, do you want to?
Yes,
Yes, go ahead.
thank you very much, Professor Jocelyn. It was very inspiring. It's an honor for us. I am also in the chapter of Women in Radio Science with Christina, and for us it's a huge honor to have you here today. So thank you very much.
Thank you.
And I would like to ask you if you think that the development of the strategies for parity during all these years have made a huge change, or do you think that there is still a lot to do in this thing? Thank you.
Thank you. I think clearly there is still work to do, because at least in Britain, if you look at a physics undergraduate class, there will be 45 men and 5 women. And, you know, it's not equality. And I really see no reason why it should be like that. I think it is social forces. Maybe more of these men would like to do art subjects, English literature, you know. Maybe more of these women would like to do science. But clearly, I think there is no reason why more women should not do physics, bits of physics. Physics and engineering are the 2 subjects in Britain where there are the fewest women. Chemistry has more women. Biology has lots of women. What's wrong with physics? So we keep trying. And there are schemes in Britain and now also in the USA where the numbers of men and women students in science subjects are regularly counted and monitored. Is the gap closing? Is the gap increasing? So there is concern. But finding a way to change society, because not only do you have to change the students, you have to change their parents, their cousins, their uncles and aunts, their grandparents, everybody. It's coming, but it's very, very slow.
Yeah.
Is it the same with you?
I think from my experience, I studied 1 year in Germany, and I saw more different, less parity in Germany than, for example, in Spain. I don't know why, but still here in engineering, I am in the telecommunication school of engineering in Malaga, in the south of Spain, and the ratio is more or less 20% of women and the rest of men, which is not bad compared to other countries, but still it's very low. Yeah.
Yes. There's interesting data from the International Astronomical Union. They have recently moved away from having just male and female, so I can no longer do this analysis. But until this year, they published data for each country how many female astronomers, how many male astronomers. And Southern Europe is better than Northern Europe. South America is better than North America. Russia is good because so many men died in the war in Russia. Women have always done things. Japan is always the worst.
Yes.
It's quite interesting.
It's cultural.
Mm.
A very last, sorry, Elena, very last question, and we need to close the session. From Leonor Anna, what would you say to girls and women from rural areas who love science but feel there's no place for them because they lack academic studies? What would you tell them to encourage them to keep going?
Yeah. We have problems like that in some parts of Britain as well, some of the more remote parts. It needs strong government policy. It needs to make sure that the educational system for people who are remote is as good as the educational system for people who live in big cities. And it does not always happen, I'm afraid. But there are more and more remarkable women studying physics. It's great, but it's slow.
Okay, it's been a pleasure to have you here. We would be delighted, as I told you, if you wanted to come to visit Spain, to come to visit the Jeves Observatory anytime that you have that you want to enjoy the good weather and forget about the rain. And thank you very much for being with us today and sharing your fantastic stories and experience. Thank you very much, Jocelyn.
Thank you all for listening. Thank you. Have a great day.
You too. Goodbye.
Bye-bye.